In this video, we see that our summand is a quantity we do not have a formula for. We're adding up a bunch of logs. There are ways you can get a closed form expression for this. However, determining the asymptotic complexity of that closed form expression becomes a bit of a nightmare. So we're going to need to come up with some other technique for when we do not have any nice formula for our summation. How are we going to deal with this? We will see that we are going to, rather than use a formula, immediately start bounding the summation itself. So, to begin with, I'm going to write out what does this summation represent. We're going to write out the terms of the summation to try to justify what we are doing. So T of n is equal to log base 2 of 1 plus log base 2 of 2 plus keep going until log base 2 of n minus 1 plus log base 2 of n. And now we want to try to bound this quantity above. It's not necessarily obvious how we do this, though. One technique we could notice is that we have a bunch of terms in the summation, and there's one that is definitely the biggest term, and that's that log base 2 of n. So I'm going to try to bound this above by replacing each of these smaller terms with the biggest possible term that appears inside of that summation. So replace every single term with the biggest thing that shows up. And that definitely should always work, because log base 2 of n is always bigger than everything in that summation. By definition, for any value of n, it is the biggest thing. Log is an increasing function, so the bigger value we plug in, the bigger it gets. So, that seems like a good idea. However, this doesn't seem like it's obvious how to analyze it, but we're going to do this with the summation notation instead. So this is our idea. How can we replicate that idea using the sigma? So, T of n is equal to the sum from I equals 1 to n of log base 2 of I. I want to bound this above using the technique I just did. If you look, I replaced every single value with n. I'm going to do the exact same thing, but with the sigma notation. I'm going to replace I, which represents the different values that I'm adding up, with n. So this is less than or equal to the sum from I equals 1 to n of log base 2 of n. That's the first thing we did there. And now it becomes a little more obvious how to analyze this. Notice, I is the summation index. It is the variable that appears at the bottom of the summation. Therefore, log base 2 of n is effectively a constant as far as I is concerned. As you plug in different values of I, log base 2 of n does not change. So, just like we saw when we had the summation of 5, this is a similar thing. We have the summation of log 2 of n, but I does not show up. So, this is less than or equal to, or in fact exactly equal to, if we have log base 2 of n, we need to compute the number of terms in that summation. There are n terms in the summation. That's the top bound minus the bottom bound plus 1, n minus 1 plus 1, times log base 2 of n. So, this is an upper bound. It's a number times n times log base 2 of n. 1 times n log base 2 of n. So, this work I have done here shows that T of n is in big O of n log base 2 of n. The question now becomes, can I match this as a lower bound? Remember, you can always bound something above by too big of a function. You could bound n by n to the 5th. N to the 5th is definitely a bigger function. That is always something you can do. We want to make sure that we didn't make this too big. It seems like we might have, right? We started and replaced every single thing we added up with the biggest one. That seems like it might not work. So we need to try to find some way to bound this below and show that it is an omega of n log base 2 of n. So that is now our goal. So to bound this below, what are we going to do? Well, we need to go back to the drawing board and start with the given summation, the sum from I equals 1 to n of log base 2 of I. The technique we're going to use here is non-obvious as a start. However, it is very useful. For our upper bound, the technique we tried was to replace each term with the biggest term. Let's try something similar for the lower bound. If we try that here, we replace each term with the smallest value, that's I equals 1. So if we replace every single term with log base 2 of 1, this is a catastrophe, because log base 2 of 1 is 0. So this is equal to 0. Which we clearly already knew that summation was positive, so this is a useless lower bound. It tells us nothing. Maybe you go, well, we can ignore that and we'll plug in 2. So let's try that instead. Because log base 2 of 2 is 1. That's a different value. So what does this equal? This is the sum from I equals 1 to n of 1. That's n terms, the top bound minus the bottom bound plus 1. Times 1, the inside of the summation, just like we did before when we had log base 2 of n inside. This is unfortunate, because that does not match our upper bound. Our goal is to show that this is an omega of n log base 2 of n. And by doing this, we've made it too small in some sense. We made it bounded below by n, which may be a valid lower bound, but we want it to match our upper bound. So this does not work. So we should not be doing this. Instead, what we're going to do is we're going to split the summation somewhere in the middle. We're going to write it as the sum from 1 to n over 2 of log base 2 of I, plus the sum from I equals n divided by 2 plus 1 to n of log base 2 of I. This technique is very not obvious. You would not come up with this on your own. However, once we see it, hopefully we can understand that this is a helpful thing to do. So what we want to do is we want to make this smaller by plugging in that bottom bound. Like we mentioned before, log was an increasing function. So by replacing every single value in the upper bound with the largest value, we made it bigger. Similarly, because it's an increasing function, to make it smaller, I would have to replace everything with the smaller value. So what I'm going to do is bound this below by taking the first summation and plugging in the bottom bound for I. By doing that, every single term there is definitely bigger than log base 2 of 1, because they're log base 2 of 1 plus log base 2 of 2 plus log base 2 of 3, and so on and so on and so on. And each of those values is bigger than log base 2 of 1, which actually turns out to be 0. Plus the sum from I equals n divided by 2 plus 1 to n of log base 2 of n over 2 plus 1. And again, the exact same reasoning holds here. The first value of that summation is log base 2 of n over 2 plus 1. The next one is 1 bigger than that, then 1 bigger than that, then 1 bigger than that, then 1 bigger than that. Each value is bigger than or equal to n over 2 plus 1. So by replacing I with n over 2 plus 1, we make it smaller. It turns out we actually never need that first summation. Log base 2 of 1 is 0, so it will go away in this problem. But in general, we didn't need to keep this summation at all. So we're just going to not write it down. Even though it's equal to 0, if it wasn't equal to 0, we still do not need it to make our lower bound match our upper bound, it turns out. So we're going to drop that summation we are going to drop that summation in its entirety. So let's write down what we have. We have that this is greater than or equal to the sum from I equals n divided by 2 plus 1 to n of log base 2 of n divided by 2 plus 1. I'm going to do something at the same time here, which is that plus 1 inside of the log is just going to be tedious. And when bounding below, you can always, always, always drop constants that are added on. So I'm going to drop the plus 1, which makes it yet smaller still, because n over 2 is definitely less than or equal to n over 2 plus 1. Now, I, just as we did in our upper bound, have a term that no longer has any i's inside of it. This has no I inside of it, which means it is effectively a constant so far as the summation is concerned. So I'm adding up a fixed quantity, log base 2 of n divided by 2, a certain number of times. The number of terms in a summation is, again, the top bound minus the bottom bound plus 1. So this is greater than or equal to the top bound minus the bottom bound plus 1 times the summand, the thing inside of the summation, log base 2 of n divided by 2. And this actually simplifies in a nice way. We have n minus n over 2 is n over 2. We have minus 1 plus 1, which cancels in a way that makes me very happy. So we have that this is greater than or equal to n divided by 2 times log base 2 of n divided by 2. We're not done, unfortunately, because the inside of that log is not exactly log base 2 of n. We need, remember, to show that it is an omega of n log base 2 of n, we need to reduce this to a constant times n log base 2 of n. It is not exactly verbatim log base 2 of n inside of that log, so we have more work yet to do. There are two ways to analyze this. We saw this when we analyzed logs in the past. We can either replace n over 2 with log of n minus log of 2, or we can replace n over 2 with a quantity that is smaller and has some convenient properties. So what I'm going to do is observe that n over 2 is bigger than or equal to radical n. I'm going to square both sides of this, and we get n squared over 4 is greater than or equal to n. We then multiply by 4 and on both sides and have n squared greater than or equal to 4n. Divide by n on both sides, and we have n greater than or equal to 4. So, if n is greater than or equal to 4, we have a certain condition of how big n must be. We can replace n over 2 with radical n. Let's do that. This is greater than or equal to n over 2 log base 2 of the square root of n, and that's true when n is greater than or equal to 4. And now, radical n is n to the 1/2. So we can pull that 1/2 out front of the summation, and we have that this is greater than or equal to n divided by 4 log base 2 of n, which is a number 1/4 times n log base 2 of n, which was the goal. Remember, we wanted to show it was an omega of n log base 2 of n. So t of n is in omega of n log base 2 of n, and O of the same n log base 2 of n. Ignore the page number I have to write by there. Thus, if it's an O and omega of the same thing, it must be in theta of that said thing. So thus, t of n is in theta of n log base 2 of n. It seems like we did a lot of weird trickery in this problem, but this technique is surprisingly robust if we just follow this idea. When you have a summand that is an increasing function, log base 2 of I is an increasing function of I. When that is the case, you are going to split the summation in half, drop the smaller half, and replace I with the bottom bound. So this technique that we used of split it in half, then plug in this bottom bound for I, and then simplify, will work for a large variety of summations. We will see exactly one instance where this will break, and we'll comment specifically on that. Similarly, our upper bounding technique of replacing each term with the largest is, again, surprisingly ubiquitous. We are going to be able to use that for a lot of different summations. So, this idea of replacing log 2 of I with log 2 of n, plugging in that top bound, replacing each term with the largest, is again going to work in a surprising number of cases, except for one instance. So, while this may have seemed like, why on earth is he doing the following steps, the goal of trying to bound this below is to develop a technique that will work for a large swath of functions, and this technique will do that. Notice, the dividing by 2 here was arbitrary. You can split this anywhere. Between 1 and n, that is a fraction. I could have chosen n divided by 3. I could have chosen 3n divided by 4. I could have chosen n divided by 86. It does not matter. However, we choose n divided by 2 because it is a nice number, and it theoretically only requires that n is at least 2 for it to make any sense. We didn't specifically comment on that. However, we may have needed to at the end. But n needed to be at least 4 already, so n divided by 2 is definitely bigger than 1, so this was a valid technique to do.